So today we're going to be beginning this completely new unit in math, and it's one that you probably really haven't ever even seen before, and that can be a little scary. So I want to encourage everybody to be really open-minded as we start this. And just as we've done before, we're going to take a nice deep breath before we start this, and then we'll dive into it. So we're going to be talking about these things called vectors, and eventually we're going to tie numbers to those things. But until we get to that point, and in this first lesson, I really just want to focus on kind of the geometry and the diagrams for how vectors work. So we're gonna dive into that and sort of we're gonna get through it. As is almost always the case in math, when we're learning something new, we need to start with definitions. And so if we're going to talk about vectors, we need a definition, right? So a vector is, for lack of a better term, a mathematical object, right? A number is an object, a variable can be an object. So a vector is a mathematical object, and this mathematical object contains information about the displacement from one point to another. Put into other words, particularly if you've seen Despicable Me, a vector tells us effectively the distance and the direction. Sometimes another word for distance is magnitude. So a vector basically tells us the distance and the direction needed to travel from one point to another. So a vector is this mathematical object that contains information about a direction and a distance. Okay? Now you guys also know that we need to talk about notation. Okay, so a vector that represents the displacement starting at A and going to B is most often denoted AB with an arrow over the top of it. So AB with a little arrow over the top. Okay. As far as diagrams are concerned, when we draw diagrams of vectors, we generally draw them as a line segment that has an arrow on one end pointing in the direction of the displacement. So if you have point A over here and point B over here, we would draw a diagram of this by connecting A and B and putting a little arrow at the end of it. I do want to point out that this is different. Like you guys may remember learning in some earlier class about rays. Like the ray AB is the idea of a segment, or not a segment, but like half of a line that goes through A and B and then on for infinity. Okay. A vector is not infinitely long. That's not what we're talking about here. When I draw this arrow, I'm literally talking about this vector being this direction and that length. So the arrow on the end is telling you that we're going this way, like at that angle, and I'm using a vector that's that length. Okay. So that's sort of diagrammatically and definitionally, this is sort of what a vector is and where we're going to be starting from. So now that we've sort of got some of these basics established, we need to move on to talk about several properties of vectors geometrically. So when you very first learned about numbers, like as a little kid, you would maybe talk about when are numbers equal to one another. You might have talked at some point about negative numbers. At some point you talked about adding numbers and subtracting numbers. When we introduce a new mathematical object like a vector, we begin asking those same questions. When are vectors equal to one another? What does the negative of a vector mean? What does a multiple of a vector mean? How do we think about adding and subtracting these new mathematical objects? So that's really where we're going to be going next. This whole video is going to sort of be about what are the operations that we can do with vectors, not using numbers, but thinking about it geometrically as distances, as displacements, as magnitudes. So the first of these properties that we're going to talk about is this idea of when are vectors equal or equivalent to one another. And a key point that I want to express to you is that a vector just represents direction and distance. It tells us absolutely nothing about the actual starting and ending points, right? And to give like a real world example for this, like a vector in the real world would be like me describing 5 meters north. Like if I say 5 meters north, I could be talking about 5 meters north of room 406 at school. I could be talking about 5 meters north of the fountain in the courtyard. I could be talking about 5 meters north of the grocery store. Like I could be talking about 5 meters north of anywhere. And so the actual starting and ending points are really not, they're not told by vectors. Vectors are just about the direction and the magnitude. And so what that means is any vectors that represent the same distance and the same direction are equal vectors. Now, in this lesson, I'm going to be using this diagram right here a lot. Right, so like for the next slide on like 4 examples, we're going to keep looking at this diagram. Parallelograms make it really, really easy for us to sort of see things that are the same and see relationships. So we're going to do a lot of things with one diagram, and then we'll do some things with a different diagram later. So for each of these vectors here, I want you to look at the diagram and find another vector that's the exact same thing as that vector. Okay, so let's go ahead and go through A together. So the vector AB is this thing right here. It sort of represents that distance and that direction. Do you see any other vectors that are the exact same length and going in the exact same direction? Well, hopefully you notice right down here, DC is exactly the same thing. So we could say that vector AB is exactly the same as vector DC. And I don't mean like, oh, like they're similar. No, they're literally the same vector. And you might say, well, wait, but that's weird. This one's on top and this one's on the bottom. Remember, a vector does not tell us anything about where it is. It just tells us about direction and magnitude, direction and distance. Okay, so try the next one of these out on your own and see if you can get this. So DA, I'm going to use a different color here. So DA is basically that distance and that direction. Well, hopefully you can see pretty clearly that's the same thing as vector CB. Okay. The next one that we could do here is BE. So let's hear BE. BE would be from here to here. Are there any other things in the diagram that are like the exact same direction, the exact same length as that? Well, the diagonals of a parallelogram bisect one another. So basically that vector is the exact same thing as this one right here, ED. And then the last one that I have here is the vector EA. Well, let's see here. EA is that vector right there. And so CE would be the exact same thing. Okay. And so I want to sort of point out to you guys, lots of times when you're looking at diagrams, you're going to find that the same vector is used with different names in different places. But because they're the same, you can sort of replace them with one another. So this idea of recognizing when vectors are the same is going to be really, really important to our development and our ability to solve problems. In this next slide, I want to talk about like the negative of a vector and scalar multiplication. So we're going to sort of go through these two things at the same time. So the first one, this is this key point. We understand the negative of a vector as a vector that has the same length but the exact opposite direction. Okay, so if I had the vector that went from A to B, right, and so there it is, there's vector AB, we would understand that the vector negative AB should just be a vector that goes, the exact opposite direction. So the exact same length that we had over there, but it's going in the opposite direction. But if you think about it, wouldn't that be the same thing as instead starting at B and going to A? And so I wrote this up above. This is something that we actually often write. If somebody says the negative of a vector, you can just sort of switch around the order of the letters that are there. Okay? So I hope that made sense in terms of negative vectors. When you have the negative of a vector, you're just talking about the same vector going in the opposite direction, which means you can actually rename it to make it a quote-unquote positive vector. Okay. The next thing I want to talk about is called scalar multiplication. Okay, and the word scalar is really just a fancy word for a number. Okay, so scalar multiplication is the name given to the process of multiplying a vector by some scalar. Okay. Scalar multiplication, the notation is that you put a little, like a k, and k is a constant. So you could put 3 there, or 2, or a half, or -5, where k is a scalar. And what that's going to mean is it's going to mean that the vector AB is scaled by a factor of k. So if k is 5, it's going to take AB and scale it to be 5 times as long. If k is a half, it's going to scale it to be half the length of AB, but keeping the same direction. So I'd like you to think for a moment, what would 2mn represent? Like pause the video for a moment, maybe write down like one sentence. What would 2mn mean? Maybe you could even try and like draw a little picture of it. So I'm thinking here that 2mn is a vector that's in the same direction as mn, but is twice as long. So for instance, if this were the vector m n, then 2mn would sort of be, that, and then twice as. So I tried there to sort of make it so that this thing was twice as long, but sort of parallel to, with the same direction as mn. And then think through the same thing. In your own words, what would 1/4 dc represent? Well, hopefully you've got here the idea that this is going to be a vector in the same direction as dc, but only a quarter as long. And so, for instance, if the vector dc were doing this, where this is d and this is c, then a quarter dc would be me sort of trying to draw the same direction, but only about a quarter of the length. Okay, so a scalar multiple is really just this idea that when you put a number in the front, you're sort of scaling the vector with the same direction to be shorter or longer by this scale factor. I mentioned earlier in the video that we were going to be using this parallelogram a lot, so here it is again. I'd really like you guys to try this one as much as you can on your own, and then let's check in together. So part A, write down two vectors that are equivalent to a half dB. Well, let's see here. dB is here, so a half of that feels like it could be dE or EB. So great, dE and EB are both the exact same thing as a half dB. They're both a half the length of this thing. Yay, wonderful. So next, draw on this diagram, or in another space, what would negative 2AB look like? Well, let's see here. AB is this right here. So negative 2 of that would be the thing that's twice as long as that in the exact opposite direction. So I'm going to sort of draw it over here. It would be like, that's okay, so that seems like it's about twice as long, and it's just going in the exact opposite direction. Okay, this first one here was sort of horizontal and pointing to the right, so I made this one horizontal but pointing to the left, and my goal was to make it about twice as long. Okay, question C for this one. The point F is such that AC equals half of CF. Draw the approximate location of the point F. Okay, so AC, so let's hear. They're saying that AC is half of CF. So if AC is only half of CF, I mean, another way to actually write this, couldn't we write that CF is 2 times AC? Like, just imagine multiplying that, like multiplying 2 to both sides of this thing, right? So now we go, oh, well, if CF is twice AC, this is AC. I would just use twice that AC, and so approximately that's where the point F is. Okay, so the idea here was that I took the idea of the direction and the length of AC, and I used it not once, but twice to get me from C down here to F. Okay. This idea of thinking about vectors geometrically and with diagrams is a really, really, really big part of this whole vectors unit. So that's why I'm sort of taking time going through these little small pieces and building our skills up. All right, so just to recap so far, in our lesson up to this point, we've covered what a vector is, we've covered how to multiply them by numbers, and we sort of talked about negatives. By the way, you might be wondering, can we multiply vectors together? We are going to get there later. So just hold that thought. We'll get there eventually. The next operation that we want to understand is addition, and after that we'll go to subtraction. So because this lesson is about thinking about this geometrically and diagrammatically, I want to start with a key point about that. Geometrically, we can think about adding vectors as placing vectors head to tail and then drawing the resulting vector. So let's say, for instance, that this is what vector AB looked like, and this is what vector CD looked like. And somebody said, hey, what's AB plus CD? Okay, what you would do is you would just imagine, okay, well, here's what I'm going to do. I'm going to start at A, and I'm going to follow that thing up to B. That should have maybe been a little bit longer, oh well. And then I'm going to take this direction of CD and go, yep, I'm going to use that thing to get down to here. And then this is the sum of those two vectors. Okay, so sort of to put it into those terms, and I can't give a name to what this thing is, but if this is AB and this is CD, then this vector that I drew down here in black, this is the vector AB plus CD. Okay? Now, some of you might be worried. You might be like, whoa, 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 wait a minute. But like this length plus this length is definitely longer than this length. I agree. But remember, this is all about displacement, right? And you can almost think about this like taking a trip, right? If this is home and this is school and this is you stopping somewhere along the way, right? The path that gets you from home to school and the path that stops along the way and gets you to school still gets you from home to school. They're both expressions of the same resulting displacement. So don't be worried about the fact that one of these paths is longer than the other. What's important is that they both have the same starting point and the same eventual ending point. Okay? So to recap this slide, if you're thinking about adding vectors, what you do is you imagine taking the first vector, putting the second vector right on where the arrow of the first vector left off, and then drawing the resulting vector in between them. Here's our favorite parallelogram again. We've got this diagram of a parallelogram, and I'm going to ask you these 4 questions. So first, I want you to look at the diagram and sort of, draw a picture of, and then write down the result of what is vector DE plus EC. Well, if I did DE plus EC, well, those ones actually already are sort of like the arrow of this one lands right at the beginning of the other one. So that thing is going to result in the vector DC. So this thing is DC. Yay. What about BE plus CE? BE plus CE. So let's see here. If I did BE, now CE starts over here. Well, wait, but that CE, that CE is the same thing as this right here, isn't it? So BE plus another name for CE shows me that this is really just me going from B to A. Okay. Now this next one is maybe a little circuitous. Let me see if I can actually erase what I've drawn so far. Oh, great. Let's get some space back on this diagram. So DC, so let's see, they want me to go from D to C, then from D to A. Well, wait a minute, D to A is the same as C to B, so now I'd be following that path, okay. And then they want me to go from B to A. Well, wait a minute, if I went from D to C, and then basically from C to B, and then from B to A, what is that all effectively the same thing as? Isn't that the exact same thing as just going from D to A? Great. That's what that vector is. Okay. And then finally, the last one that I have here, I want us to draw the result. Oops, looks like I can only erase some of that. Draw the result of doing AC plus DB. Okay, so AC plus DB. So now they want me to take DB. So if I sort of imagine taking this thing and putting it over here, right? The resulting vector would be from here over to here. Okay? Now, using your knowledge of parallelograms and similar things and all that, can you give that vector a name? Like, can you recognize what that is in terms of other letters in this diagram? I'm going to let you think about that for a second. And if you're having trouble thinking of it, I want you to imagine for a second, what if you took this parallelogram and then just put another one of them right next to it? Do you see how adding those two diagonals together basically gives me 2AB? This is AB. This is just 2 of them in a row. Now, I know this is a new topic, and I hope that this isn't super confusing, but if it is, I hope that you'll be writing your questions down and being ready to ask me those things. Like, we're going to take a lot of time to build these skills up, and we're going to get really, really good at vectors, but we got to start small. Alright, so if you've understood everything so far, subtraction of vectors is really just combining our knowledge of addition of vectors, which means putting them like head to tail, with our knowledge of the negative of vector, which means them going in the opposite direction. So if anybody ever asked you to do like mn minus ef, you could just say, well, wait a minute, negative ef is fe, so I just add that thing on, right? I do want to throw in one quick definition here, and that definition is that there's a thing called the zero vector, right? And the 0 vector is not the same thing as the number 0. Okay, the number 0 means the number 0, and the 0 vector means a vector, not a number, a vector that has no direction and no length. Okay, an example of its use would be if you had the AB vector and then subtracted the AB vector off of it. In other words, if you're like, hey, I'm going to go from A to B, and then I'm going to subtract AB. So if I'm going to go from A to B and then go from B back to A, I would just wind up where I started. That's the concept of a 0 vector. It's the concept of, hey, everybody, I'm at A, and I'm not going anywhere. Okay, that's what the 0 vector is. Okay? So this is going to be the last time that we look at this parallelogram in this video. Okay, so again, I would really encourage you guys to pause the video, try this out on your own, and give yourself a chance to see whether or not you can get these on your own. So first, as we've done in the similar examples, in the previous examples, write down the result of AB minus CB. Like what is that? Right? So AB minus CB, that would basically be AB plus BC. So AB plus BC, oh, well, that would just take me from A to C. So this is AC. Okay. Next, what about DE minus EA? So DE minus EA, and again, if you haven't tried one of these on your own, give it a shot. So this is DE minus EA. So DE, that could be DE plus AE, DE, and then plus A to E. I really want to put the beginning of that thing where this one is, so I'm going to take that vector and recognize that's the same thing as EC. So you could even write that as another step. This is the same as DE plus EC, and we can see really clearly that that's just DC. Okay? And then the last one I have here is to ask us to find DC minus BC. So let's see here, DC minus BC. We could rewrite that as DC plus CB, right? So DC plus CB. That looks like that's really straightforward. That's just DB. Okay. As far as diagrams are concerned, these are the kinds of things that you can do to find the relationships between vectors. In the next video lesson that I'm going to do in this subject, we're going to learn how to associate numbers and algebra to vectors. But for now, we're really just focusing on this geometric interpretation. Throughout this chapter, we're occasionally going to encounter problems without numbers, and those need to be solved geometrically or abstractly. So I've got one more example of this, one more like slightly harder example that's going to sort of put everything together. So stick me through that one. We'll try that one out, and then you guys will be ready to try some of these on your own. So all of the notation that we've used for vectors so far has used two letters with an arrow over the top of them. Sometimes in a problem, though, you're going to use a vector so often that you want to give it another name. And so very commonly, they'll just use one lowercase letter also with an arrow over the top of it. So this is an example of that. So this diagram shows a parallelogram, a different one now, a different parallelogram, the A, B, C, D. And they're saying let, so they're defining the AB. Oh, whoops, I just realized. Oh, no, I did it right. Okay. So AB is going to be the vector little a, and AD is going to be the vector little b. M is the midpoint of CD, and N is a point on BC such that CN is the same length as BC. Okay, so that's sort of all of our setup. Now the question, what we're being asked to do, it says express all of these vectors in terms of A and B, which means every one of these answers is going to be like A plus B, or a half A, or 5A minus 3B. That's the kind of thing you're going to be looking for here. So why don't you go ahead and try like A and B on your own, and then we'll sort of check in and make sure you've got those, and then we'll make sure you can get the other ones. So CM is right here. It looks to me like CM is like half of CD. And so we could even write that down. We could write down that this is half of CD. But CD is the exact same thing as BA, right? Like CD right up here at the top, that thing's the same as BA. But we know that BA, this would just be negative a half of AB. And we were told in the problem that AB is little a. So we could make this negative 1/2, running out of room here, negative 1/2 the a vector, and that's our answer for a. Okay, what about bn? Right, and I showed a lot of work here. I don't know that you need to show all of that for all of these problems, but it's important for us to see that we can do that, especially as these problems get harder. And I guarantee you, these problems are going to get challenging by the end of the chapter. We're going to want these skills. So bn goes from here to here. Well, I mean, that seems pretty clearly to be just twice the b vector. So this is 2b. Okay, now what about getting from b to d? Okay, let me use a different color here. If I wanted to get from b to d, I feel like I could use this vector backward, and then I could use this one. Well, cool. So I could just write negative a plus b. Or in other words, b minus a. Either one of those things would be acceptable. Okay, let's look at mn. Right. To get from m to n, I feel like I would want to do this and this. Well, what are those things? MC, actually, that's actually kind of funny. We did CM up here. We found out that that was negative 1/2 a, so this would just be 1/2 a. So 1/2 a plus this thing. Well, we already decided that was the same as that, which is the same as that. Oh, that's just b. Okay? And then the very, very last question in here, I know this has been a long video, this has been a long introduction, but we're almost there. On the diagram above, let's label the point P, which is the midpoint of AC. Okay, so label the point P, so the midpoint of AC. So there is P right there. So this is P. Okay. Express NP. So if I wanted to get from N to P. I feel like if I wanted to get from there to there, I would go from like N to C, and then maybe I would go like halfway down this one, and then over. Right? Couldn't I see that as this first one, which was the negative b vector, and then minus another half of the b vector, and then this here, which is minus a half of the a vector. So this looks to me like it's negative 1/2 the a vector minus 3/2 the b vector. This is the kind of reasoning that we can do with a geometric understanding of vectors. So I hope that made sense. If you've got questions, please ask them. This is a really fascinating chapter, and I hope you guys get a chance to enjoy it. So best of luck as you try the exercises and the assignment on your own.